Welcome everyone to this online session. Today we have the honor of having Klaus Aschenbrenner with us, and Klaus will present himself in a few seconds. Myself, I'm Brian. I'm the host for today, and welcome to this user group. We will have a theme of GUIDs as primary keys, and I'm really looking forward to this session from you, Klaus. After this session, you will get a automatic email from Meetup. I hope that you will answer to it, because we would really love to get better. If you have any questions, any ideas for us, then please let us know. And if I sound groggy in my voice, then that is the reason, because I was just hit by Corona the second time. So that's why. So if I'm blurred out or something, then you know why. So over to you, Klaus, and I'm looking forward to it.
Thank you. So welcome everyone from my side. I hope that you had a nice day. And now over the next 75 minutes, I want to talk about one of my favorite topics in SQL Server, unique identifier values as primary key values. A few words about my person. My name is Klaus Aschenbrenner. I'm based in Vienna in Austria, and I provide with my company SQL Passion, SQL Server consultancy and training services across Europe. I'm a Microsoft certified master for SQL Server. I have also written the book Pro SQL Server 2008 Service Broker, which was published by April in the summer of 2008, so already a very, very long time ago. And Service Broker was introduced back with SQL Server 2005. And with Service Broker, Microsoft provides us the functionality to write message-based asynchronous database applications directly within SQL Server. Here you can find more information about my person, my services that I'm offering on my website, sqlpassion.at, where I'm also regularly blogging about SQL Server and other IT-related topics. So what is now the agenda for the next about 75 minutes? More or less, I want to give you an overview and introduction why unique identifier values as primary key values are a bad idea in SQL Server. We will start this session by talking about some basics in SQL Server. More or less, I want to introduce indexing to you. Clustered indexes and non-clustered indexes. We will see how both indexes relate to each other, and based on that knowledge, we can later understand why unique identifier values are really not a good idea for primary key values in SQL Server. Let's talk now in the first step about clustered indexes. More or less, when we create tables in SQL Server, we are dealing in SQL Server with two different kinds of tables. We have so-called heap tables in SQL Server, and we have so-called clustered tables. So imagine you have a create table statement, and you just create your table without any index. So you don't specify a clustered index, you don't specify a non-clustered index, and you are also not specifying any primary key constraint. In that case, we are talking about a so-called heap table. A heap table has a huge advantage. Writing to a heap table is very, very fast because you have physically not structured the data in your heap table. So it's up to SQL Server where SQL Server puts the records which you are inserting into your heap table. So a heap table is very, very fast for writing because we don't have to maintain a sorting order. And that's also the drawback of a heap table. We don't have a sorting order. That means when we want to find a record in a heap table, SQL Server has to go through the whole heap table to find corresponding records. In the case of SQL Server, when you look in the execution plan, that's a so-called table scan operator. And the table scan doesn't really perform quite well because the more data you have in your heap table, the longer and longer the table scan operator just takes more and more time. And therefore, we have also the possibility in SQL Server and also in other relational databases to create a sorting order for our table. And then you create a clustered index on that table, means that SQL Server transforms your heap table into a clustered table. So when we talk about a clustered table, it just means that you have on your table a clustered index defined. And as you know, when you create a clustered index, you have to specify a so-called clustered key column. That's just a column, and that column specifies on which columns we are physically sorting our table data. Means when we are searching for records in a clustered table, the search operation is very, very fast because we have a sorting order, and based on that sorting order, we can find records in a very, very efficient way. That's a clustered index seek operation in the execution plan of that query. So that's a huge advantage. The disadvantage of clustered tables, on the other hand, is that we have to maintain that sorting order. Means when we insert a row into that clustered table, SQL Server has to find the correct physical position where that row has to be inserted into that table. And therefore, a clustered table is more or less very, very slow for inserting records when you don't insert records at the very end of your clustered table. Imagine you have a phone book and you are inserting a new person into that phone book. Imagine like my last name, Aschenbrenner. It's at the very beginning of that phone book. When you insert that record into your phone book, you have huge problems because you have to rewrite your phone book. You don't have some free space available for my last name. And more or less the same things are applying to SQL Server. So SQL Server has to make so-called page splits to make some free space in your clustered table. And that page splits are taking a lot of time. And as we will also see, page splits are introducing a so-called external and internal fragmentation in your clustered table, and both fragmentation types are not very good. And when you think now, when you have your clustered key, your clustered index on a data type with random values, like a unique identifier value, you are inserting random values sorted into a table. So this is already somehow a contradiction. We are inserting random key values in a sorted order into our table, into our clustered table. This can't work quite well, and we will see that later. So this is already very, very important that we have two types of tables in SQL Server. A heap table is a table without a clustered index, fast for insertion, slow for reading. And a clustered table is just a table where we have defined a clustered index. You can only have one clustered index on a table, and clustered indexes, clustered tables are very, very fast for reading, but on the other hand, they are very, very slow for writing. So when we now look on a clustered index is a so-called B-tree structure in SQL Server. The B stands for balanced. So SQL Server uses internally a so-called balanced tree, a B-tree structure. And in that B-tree structure, we always have a so-called index root page. That index root page is on the top of that index, clustered index. And based on that index root page, we can go now to pages in the levels below and find corresponding records into or in that clustered index. A page in SQL Server is always a unit of 8 kilobytes. Means when we are inserting rows into a table, SQL Server structures our table data in pages of 8 kilobytes. This is also very, very important for your database design. Means the smaller your records are, the more rows you can fit into one page of 8 kilobytes. So this is also very, very important, because on the lowest level, SQL Server performs I/O operations on the page level. Means the more rows you can fit onto one page of 8 kilobytes, the more rows you can transfer with one I/O operation between your slow storage subsystem and your fast main memory. So in that slide, we have a clustered index in front of us with 3 levels. You always have an index root page. Then you can have multiple so-called intermediate levels. And finally, you have a so-called leaf level. The leaf level is at the very bottom. And in that leaf level, we have our table data. And that table data is sorted by our clustered key column. Means when you have a clustered key, a primary key, we will talk later about the differences between a primary key and a clustered key. But when you have a clustered key on a random value, then you have physically pre-sorted your table data on that random key value, like a unique identifier value. And that's not a really good idea. So let's switch now to SQL Server and let's have a look on clustered indexes. So I'm creating here a new database, and I'm creating here now a very simple table definition. As you can see, we have here a customers table, we have some columns, and when we do the math, that record that we are describing in that table definition has a row size of 400 bytes. Means, as I've said, a page in SQL Server is 8 kilobytes large. Means with a row size of 400 bytes, we can fit 20 rows of 400 bytes on one page of 8 kilobytes. And as you can see, I'm using here as the first column data type a unique identifier column. And I'm specifying here the primary key constraint. This is already now very, very important. Primary key, what is a primary key? A lot of people are thinking that the primary key and the clustered index or a clustered key are the same thing, but that's not the truth. I have started around 20 to 25 years ago working with SQL Server. I have started as a .NET developer, and more or less back in these days, I had no idea about SQL Server. I have thought about SQL Server just as a database, data input, data output, and I didn't care about performance. Sometimes my database applications were fast, then I was very, very happy, and sometimes my applications were slow, and then the root cause for me was always SQL Server. It's not me, it's always SQL Server. But I was completely wrong. More or less, it was just me because I have made bad things in SQL Server. And trust me, I have used a lot of database designs, or I have created a lot of database designs where I have used unique identifier values as primary key values, because from a developer perspective, they are great. We don't have to go to the database to generate our unique value. We can generate that unique value directly in our application, directly inside the application layer without going to that database. So from that perspective, from a development perspective, unique identifier values are great. We can just generate those unique keys directly within our application without using the database itself. So I have always specified in my first column the unique identifier data type followed by the primary key constraint, and I had no idea what I'm doing here. And it's very, very important to understand that the primary key and the clustered key or clustered index are not the same. The primary key constraint is on the logical level. With the primary key constraint, we are telling SQL Server that we want in that column customer ID just unique values. That's the primary key constraint. And of course, we can reference that primary key column with foreign key columns. So we can create a referential integrity in our database schema. But on the logical level, we just specify or we just tell SQL Server that we want to have a uniqueness in that column. And now the question is, how can we enforce that uniqueness in SQL Server? Well, SQL Server has two different ways to enforce that uniqueness. SQL Server can create a unique clustered index, or SQL Server can create a unique non-clustered index. So there are two different data structures, two different index structures that SQL Server can use to enforce that uniqueness on the physical level. And therefore, when you look on the primary key constraint, you can see in the documentation that we have two options. You have a primary key clustered, and in addition, we also have the primary key non-clustered option. So this is very, very important. We have two different kinds of primary key constraints in SQL Server. Primary key clustered and primary key non-clustered. The problem is the clustered option is the default option. And because it's the default option, we don't need to specify it. And that's the reason why a lot of people, including myself in the past, are thinking that the primary key and the clustered index are just the same. But as we will see later, they are completely different things. The primary key is on the logical level. We just specify that we want in a specific column or in specific columns uniqueness, and the clustered index is just the table data. And sometimes the primary key can be enforced with a unique clustered index or with a unique non-clustered index. So let's create now that table. As I've said, we have here now a row size of 400 bytes, means we can fit on one page of 8 kilobytes 20 records. So let's insert 20,000 records into that table. Means with 20 records on one page, we are allocating here in the leaf level of that clustered index 1000 pages. So as you have seen in the table definition, we have used the primary key constraint. The default option is clustered, means in the background, SQL Server has created for us a unique clustered index. So we are not talking here about a heap table anymore. As I've said previously, a heap table just means we have no clustered index. But here we got on that table a clustered index because we have used the primary key clustered constraint. As you can see, when we do a select star against that table, we have our 20,000 records. So we have 20,000 records, and now I'm using here the dynamic management function systemdb index physical stats to get more physical information about the clustered index that SQL Server has created in the background for us through the primary key constraint. I'm passing in the database ID, object ID, a few other values. So let's do here a simple select. And as you can see in the type description, index type description, we are dealing here with a clustered index. So it's a side effect that we have here a clustered index created. That's the side effect of the primary key constraint. And as you can see, we got back here 3 records from that dynamic management function. And that means that the index, the clustered index that SQL Server has created for us consists of 3 levels. Means the same as we have seen previously in the PowerPoint slide. We have 1 index root page, 1 page or multiple pages in the intermediate level, and finally in the leaf level at the bottom of the index we have our data pages, and on those data pages SQL Server stores in an ordered way our records. So the leaf level of that clustered index, that's our table data. Let's have a look on those pages. We can use here the dbcc int. Int stands for index, the dbcc int command to return all the pages for a specific table in a specific database. So let's do that. As you can see, that table consists of a huge amount of pages. In sum, we have here 1477 pages. Some of those pages are index pages, some of those pages are data pages which are storing our records. Let's analyze that data in more detail. I'm creating here a helper table, and that helper table has the same structure as the output that we see here in front of us, which we got from the dbcc int command. So let's create the helper table. And with an insert into command, I'm just inserting the output of the dbcc int command into that helper table. We have done that. And now we can query against that helper table. Page type 2, those are the index pages. So let's have a look on that one. As you can see, our clustered index consists of 8 index pages. So those are just additional pages from the root level and the intermediate level. Means we have 1 index root page and 7 pages in the next intermediate level. Let's retrieve our data pages. When we go down to see the row count, do we see it here? We have 1468 rows. As I've said previously, we have a row size of 400 bytes. We've inserted 20,000 records. With a row size of 400 bytes, 20 records can fit onto 1 page of 8K. So in sum, we should allocate 1,000 pages in the leaf level. But we have allocated 1,468. Why? Well, because SQL Server has generated page splits for us. Means, as I've said, when you insert a specific key into that table, SQL Server has to insert that row into one specific location. And when you don't have a free space on that page, SQL Server has to split that page. Means SQL Server allocates a page, inserts that page logically into that corresponding slot in the leaf level of the clustered index, and then SQL Server makes the insert. Means some part of that newly allocated page is empty. It's the same as I've said previously. You want to insert a new record into your phone book. You also have to allocate a new page, and then you insert into that page a record. Of course, that page is not full at 100%, and the same concept applies here to SQL Server. So we have here almost 1,500 pages in the leaf level, but those pages are not really full. We've also seen that previously when we go back to systemdb index physical stats. SQL Server also tells us that here. As you can see, we have here a column called average fragmentation in %. We have a so-called external fragmentation of 99%. What does it mean to have an external fragmentation? External fragmentation just means that the logical and physical sorting order of our pages are not the same anymore. Of course, we still have a logical sorting order in the leaf level of our clustered index. The logical order is always there. But now the question is, where are those pages stored physically in your data file? You have the first page, you have the second page, and you have a third page. Maybe the first page in your clustered index is stored here. The second page is stored here, and the third page is stored here. Means you are getting a fragmentation, an external fragmentation. External fragmentation just means that the logical and physical sorting order is not the same anymore. Means when you access the data from your storage subsystem, you are getting random I/O instead of sequential I/O. And random I/O is very, very slow in comparison to sequential I/O. So this is the first problem. We have an external fragmentation. And in addition, we also have a so-called internal fragmentation. Average page space used in %. Those 1,468 pages that we have in the leaf level of that clustered index, every page is full at around 67%. So 2/3 of a page are full, and the remaining 30% are just free space because of the page splits. Means our table just needs more space. More space in your storage subsystem where your data files are residing. You need more space in main memory. Those pages are stored in main memory in the so-called buffer pool. Means you just need more space in main memory. When you make a backup of your database, it just takes longer because you also have to back up that free space. And the same applies when you are restoring your database, it just takes longer because you also have to restore that free space in those pages. So this is very, very important. So as you can see here, from that simple table definition, with a unique identifier value as a primary key value, we have already huge problems. Okay. Let's go back to PowerPoint. So that's the story about clustered indexes in SQL Server. So it's very, very important to know when you create a primary key constraint in SQL Server, by default, we are getting a unique clustered index in the background. But as we will see later, you can also have a unique non-clustered index. Let's talk now about non-clustered indexes. What is a non-clustered index? A non-clustered index is also structured as a B-tree data structure in SQL Server. So we have again that balanced tree, and very, very important, a non-clustered index is just a secondary index, an additional index. Means you have your table data. Your table data can be the heap table, so without a clustered index, or it can be a clustered index with a sorting order. And then we can have in SQL Server up to 999 additional non-clustered indexes. More indexes are not possible. So SQL Server supports a maximum of 999 non-clustered indexes. Trust me, you don't want to have 999 non-clustered indexes on a table. Reading is very, very fast, but you will get really, really serious problems when you're writing to that table. Imagine you are inserting a row into that table with 999 non-clustered indexes. You have to insert that row into your heap table or your cluster table, and then in addition, you also have to insert that row into every defined non-clustered index. It's the same when you're deleting a row from that table, you have to delete that row from every non-clustered index. It's the same when you're updating a row, you have to update every non-clustered index. So you're causing a huge overhead for writing. So every index can improve your read performance, but every index will also degrade your write performance. More or less, I know two extremes of database tables. I know a lot of databases without indexes. They are great because they are very, very fast for writing, and they are very, very slow for reading. And I also know the opposite. Databases with a huge amount of indexes. They are very, very fast for reading, but they are very, very slow for writing because SQL Server has to maintain all those indexes in the background. So more or less, you have to decide very, very carefully how many indexes you need for your current workload. The less indexes you have, the better it is, as long as your read performance is good enough. So this is also very, very important. So a non-clustered index is just a secondary index. It's the same as an index in the back of a book. Well, I can show you that one even. Let's take here one book. One of my favorite ones, Linux device drivers. I'm really, really crazy what I'm reading. And as you can see, when we go here to the back of the book, you have an index in the back of that book. And that index is more or less a non-clustered index in SQL Server. It means you have the book itself with some pages. Let's assume every page is 8K large. And that's the clustered index. That clustered index is logically sorted. We have here also page numbers, 214, 215, 216, 217. Those pages are logically sorted. And now you have in the back of that book an index. And with that index, you can also find some things in that table. For example, let's search for something like virtual memory. When I'm searching in the index in the back for virtual memory, I'm getting a pointer, a page pointer, where that topic is further described. That topic is further described on the page 413. And the same applies to SQL Server. When SQL Server accesses a non-clustered index, SQL Server has to navigate, or SQL Server needs the possibility to navigate from the non-clustered index into the clustered index. So SQL Server needs some kind of pointer. In the case of a book, we have a page number as a pointer, like 413 in our case. The question is now, how does SQL Server make that lookup from a non-clustered index into a clustered index possible? Well, SQL Server uses the clustered key value as a logical pointer. Imagine that. SQL Server uses the clustered key value as a logical pointer. That means now, when we have a primary key constraint, by default, that column gets our clustered key, and that clustered key gets the lookup value in our non-clustered indexes. Oh my God, this means we are polluting our non-clustered indexes with unique identifier values which are needed by SQL Server to support those lookup operations. And the unique identifier value has a huge amount of space overhead, 16 bytes. Well, now you think 16 bytes, come on, Klaus, 16 bytes is almost nothing these days. We have smartphones with gigabytes of space. Yeah, 16 bytes sounds almost nothing. But you need those 16 bytes for every record in every non-clustered index for that specific table. On the opposite, when you have, for example, an int identity column, an int identity column has in storage overhead of only 4 bytes. That's just 1/4 of a unique identifier value. This is not that much. Just think about it. We will see later, we will do some math, and there you will see that you can save a huge amount of space to make your clustered key value as small as possible. So a non-clustered index, as I've said, is structured the same way as a clustered index. Again, we have an index root page, we can have some intermediate levels, and finally in the leaf level, SQL Server points with that logical pointer, so in our case with that unique identifier value, to the detailed data which is stored in the clustered index. So we have here a logical pointer, and that logical pointer makes us some headache because we are polluting every non-clustered index with that clustered key value. And therefore, the clustered key value has to be chosen very, very, very carefully. You should not just create your primary key constraint on the first column in your table. No, you should really think on which columns or on which column do I want to sort my table data. And that clustered key column should be also very, very small. As I've said, the clustered key must be replicated in every non-clustered index. Imagine we are doing really, really worse things, and let's say we are using a character column as our primary key value. Let's say 100 bytes. And now assume we are defining on that table 15 non-clustered indexes, and we have 1 million of records in that table. We just need for that clustered key in the non-clustered indexes a storage overhead of more than 1.4 gigabytes of data. That's a lot. And now imagine we are doing it better. We are using an int identity column with just 4 bytes, as small as possible. In the same scenario, we just need a storage overhead of 57 megabytes. That's a huge difference to 1.4 gigabytes. So from a storage perspective, it makes a huge difference if you just use a very large clustered key value or a very, very small one, like an int identity column. And we also have now that strong dependency between our clustered indexes and our non-clustered indexes. And that strong dependency is because of the clustered key. And therefore, a clustered key should have 3 different very, very important topics. It should be unique. That's very important. In SQL Server, you can also create, I must be now very, very careful about my wording. In SQL Server, you can create a non-unique clustered index. Means with a non-unique clustered index, you can have duplicate key values. SQL Server makes those duplicate key values internally unique by adding a so-called UNIQUEIDENTIFIER column. It's an integer value of 4 bytes, means your clustered key gets internally 4 bytes larger. And in addition, you can also have a non-unique, non-clustered index, the default option. Imagine you have a country column in your table. Those country values are non-unique. You have some customers in Denmark, you have customers in Sweden, Germany, Austria, and so on. So a non-clustered index normally is non-unique because you can have duplicate key values. How is SQL Server making those non-unique key values in a non-clustered index unique? Well, quite easy, by adding the clustered key, because the clustered key is always unique. Unique by us or if we create a non-unique clustered index, SQL Server makes it unique by adding that UNIQUEIDENTIFIER column internally. So more or less, you are again replicating your clustered key column, clustered key values into your non-unique, non-clustered index. So that's the first strong dependency. And therefore, a clustered key should be always unique. Very, very important. And as I've said, it should be narrow, very, very small. The smaller your clustered key column is, the better the performance of your database table will be. And a clustered key, of course, should be static. Imagine you create a clustered key on a column that can be changed. Like last name. Last name changes when we are getting married and maybe later divorced. What happens internally in SQL Server when the clustered key value gets changed? Well, SQL Server has to change that value in the clustered index because the clustered index is our table data. But in addition, SQL Server also has to change that clustered key value in every non-clustered index. Because as we have said in the non-clustered index, we need that clustered key value as a lookup value. And that's the reason why a clustered key value should never ever change. It should be static. And in addition, even a fourth property is very, very important. It should be ever increasing so that you are adding records at the very end of your clustered index. Because otherwise, when you're inserting with random key values, like a unique identifier value, you have those page splits that I've already mentioned previously. And as we have already seen, page splits are leading to an external and also to an internal fragmentation. And we want to avoid that because it causes performance problems. So let's go now back to SQL Server and let's talk about non-clustered indexes.
Klaus, I have a question. If that's okay.
Go ahead.
I've built many data warehouses in my time, and sometimes the integer on the identity key is hitting the maximum values.
Yeah.
Then I try to reset it to start at negative maximum. Then is that the best solution? Because then I'm actually seeing page splits because it is adding new values on the negative space.
Yeah.
Is it better then to do something in the data warehouse dramatically, like rewriting it, or what would we do there?
Well, in that case, when you know that you are exceeding the maximum of the integer value, which is somewhere at 4 billions. I hope billions is correct in Denmark. In Austria it's millions, but you know what I mean.
Yes.
4 billions. You can use a big int. With the big int, it takes 8 bytes, so the double amount as a integer, but we can't exceed the big int.
Sure. So it is better to
because we have just too less time on Earth.
Yeah, sure. So it is better to
in that case I would
change that column to a big int.
To a big int,
yeah. Because the table is already created as an int, then I just need to recreate the table as a big int.
Yeah.
Okay, great.
Of course, SQL Server has to rewrite your whole table.
Yeah.
Because SQL Server has to change every record.
Yeah. Yeah. Then I get a table.
Functionality. Yeah.
Got it.
But a lot of people are telling me that, we want to use unique identifier values because an int identity column is just too less because we have that limit of 32 bits, which is 4 billions and something. In that case, just use a big int. You are still saving 100% of the space in comparison to a unique identifier value, and you're also dealing with an ever-increasing key value. and
yes,
that
exactly.
makes SQL Server more or less happy.
Yeah, or you could start the integer by the minus maximum.
Yeah.
Minus 4 billion. So yeah.
But normally in that case, I'm preferring the option with the big int.
Yeah, sure.
So let's talk now about non-clustered indexes. Let's create again a bad table, unique identifier value used as a primary key clustered value. Let's create that table. Let's again insert 20,000 rows. Takes a few seconds. And then in the next step, we just create an additional non-unique, non-clustered index on that table, just on a different column. As I've said previously, SQL Server supports up to 999 non-clustered indexes. When you try to create a 1000 index, SQL Server just gives you an error message, but never ever do that because SQL Server gets very, very slow for writing. And now we look again on those index pages of our non-clustered index. I haven't said that yet, but every index in SQL Server has an internal ID. When we deal with heap tables, so a table without a clustered index, and heap table always has an index ID of 0. A clustered index has always an index ID of 1, and all our non-clustered indexes are starting with index ID 2 and onwards. Means the non-clustered that we have created here has an index ID of 2. Means the dbcc int command returns us here now all the pages that we have allocated for the non-unique, non-clustered index that we have created previously. Again, we have here 311 rows. Every row is a page of 8K. Now we create again that helper table and we insert those rows into that helper table. So let's return our index root page. We have only one index root page. And what I'm doing now, I want to dump out that index root page. We have here in SQL Server the dbcc page command. With the dbcc page command, SQL Server can dump out a page of 8 kilobytes. By default, the dbcc page command doesn't return you any output. As you can see, we don't have here that much output because we also have to enable the trace flag 3604. So let's do that again. So we take here our index root page with a page ID of 1930. We pass that in. So we have the name of our database. We have the file ID. We only have one file, our MDF file with the file ID 1. We have our page ID 1930, and we have a so-called dump option, which just defines how the output of the dbcc page command will be structured. And as you can see, that's now the index root page. When we look on the index definition, we have created that non-clustered index on the column customer name. The customer name column is a character of 100. So that's the index column here. And now, as you see, we are dealing here with a non-unique, non-clustered index. And as I've said previously, SQL Server must make those non-unique key values unique. And SQL Server makes those non-unique key values unique by adding the clustered key column. And the clustered key column in that case is here our unique identifier column. So as you can see, even on the index root page, we have our unique identifier value because it's only guaranteed that the combination of both columns is unique. It can be the case that we have in the first column customer name duplicate key values. With duplicate key values, you can't perform a seek operation into that index anymore because you need uniqueness. And that uniqueness is enforced by SQL Server by adding the unique clustered key column. So every index record in that non-clustered index is now 16 bytes longer. Let's go here one level below. Let's take here page ID 1931. Let's dump that page out from the intermediate level. And in the intermediate level, we see the same thing again. We have our index column. That index column is not unique. Therefore, we have to make it unique by adding the unique identifier column over and over again. Let's take here one page, 2060, which we have here in front of us. Now let's dump that one out. And now we are in the leaf level of that non-clustered index. And in the leaf level, we see the same thing. We have our key value from the non-clustered. And now we also have again the clustered key value as a logical pointer. So that clustered key value in the leaf level of a non-clustered is always there. But in the levels above, it's only there if you're dealing with a non-unique, non-clustered index. And that logical pointer in the leaf level is just needed to be able to perform those lookup operations, to navigate somehow from the non-clustered index into the clustered index, because those are just different data structures and they are linked together with the unique clustered key value, which is in our case the clustered key, the unique identifier value. Means we're just polluting the whole non-clustered index on every level with that unique identifier value. And this just means that you're needing more space. Questions on that so far?
There's a question from Jan. Perhaps, Jan, you should unmute and elaborate, but it is just, will a combined two-column key work? Is that for a clustered or non-clustered, Jan, or?
It works, but again, the larger your key gets, the more overhead you are generating within that table.
Yeah.
So normally, as I've said, all your keys should be as small as possible. As you can see, we have here the row size 120 bytes. When we would do the same with an int identity column, we would have 12 bytes less. So 108. Yeah. And the problem are just the non-unique non-clustered indexes. As I've said, a non-clustered is normally always non-unique because we can have duplicate values. And in that case, SQL Server must make those non-unique values internally unique by adding the unique identifier column. And that's really, really terrible.
Yes. We
can, for example, create here, when we go up, a unique non-clustered. Let's create a unique non-clustered. I hope those values are unique, but I think so. Yeah, they are unique. We have an index ID of 3. So let's insert those index pages into our helper table. Let's return our index root page 2322. And now when we look on that index root page of our unique non-clustered index, we see that we don't have the unique identifier value any. Whoops, that was too much. I hate that. Now you can see quite nicely the difference. The first output is the non-unique non-clustered index, and the second one is the unique non-clustered index. And in the unique non-clustered index, you don't have the clustered key anymore, because it's guaranteed that the non-unique non-clustered key value is already unique. It's the same when we go now a level below. Let's take one page, 23, 23. Now we are in the intermediate level and the second level, so index root page. Now we are in the intermediate level, and in the intermediate level we see the same thing. First one, non-unique, non-clustered index. We have our unique identifier column. In the second one, we don't have it anymore, because it's already guaranteed that that key is unique by its definition, because it's a unique one. And in the leaf level, when we go now again one level below, let's take one. In the leaf level, we have again the unique identifier value, because here we need it as a logical pointer. Otherwise, SQL Server wouldn't be able to perform that lookup operation, means navigating from the non-clustered into the clustered index. That's the logical pointer, the same as I've mentioned previously with the book. When you go to the index in the background, you also have a page number, and that page number is used as a lookup into your clustered index. And the same applies here to SQL Server. So in the leaf level of the non-clustered, the clustered key value is always needed and used to perform those lookup operations. Perfect. Let's go back to PowerPoint. So we know now already a lot why unique identifier values as primary key values are more or less a bad idea in SQL Server. Let's talk now a little bit more how we can overcome those problems or those limitations that we have with unique identifier values. As I've already said previously, it's very, very important to know and to remember that a primary key is not the same as a clustered key. As I've said initially, when I've started working around 20-25 years ago, I've started as a .NET developer, and as a .NET developer, I have mainly worked with SQL Server databases, and I had no idea about SQL Server. And I also thought that the primary key and the clustered key is just the same. But as I've already said, it's not the same. The primary key constraint is just on the logical level. It just describes your database that you want to have, or that you want to have in some columns uniqueness, and to the possibility to create foreign key constraints on those columns. And SQL Server has to make that uniqueness somehow on the physical level. Somehow on the physical level, we have to enforce that uniqueness, because we can't trust the developers that they are always inserting unique values. We have to enforce that somehow. Means we need a data structure which guarantees by its definition that we can't insert into that data structure non-unique values. And SQL Server enforces that uniqueness just by creating in the background a unique index. And that unique index can be a clustered index, which is the default option. And in addition, the uniqueness can be also enforced with a unique non-clustered index. It doesn't really matter from a high-level perspective which index you need or which index you choose. You just have to make sure that the underlying index just gives you an error when you insert a duplicate key value. And that is guaranteed by a unique clustered index or a unique non-clustered index. So it's up to us as developers, when we create our table schema, to just decide how we want to enforce that uniqueness. But normally, as we know, we don't care about it. The clustered index is the default option. There must be some reason why it's the default option, so it's just good enough for us. And nobody cares about it. But we have to care about it. As we already know, a clustered key, which isn't sequential, which isn't ever increasing, gives us a lot of different disadvantages. As we've already seen, with a non-sequential clustered key value, we are getting those page splits, means we are getting that index fragmentation. External fragmentation means the logical and physical order in our table is not the same anymore. We have that internal fragmentation, means the pages of 8 kilobyte are not full at 100% anymore. Means with the fragmentation and the page splits, we are getting a huge overhead for the space of that table. Space in our storage subsystem, space in the buffer pool, in the main memory of your machine. But this is bad. As I've also said, think about your backup restore operations. You also have to back up and restore the free space of your indexes. Or even I've seen some scary things, as I've said. That page in SQL Server is 8 kilobytes large. SQL Server gives you from that page 8092 bytes. Imagine you create a table design with a record size of 4100 bytes. With 4100 bytes, how many records you can fit onto one page of 8K? One. Because two records would have a size of 8200. 8200 would be larger as the page size. It means in that case, SQL Server can only insert one record into one page, and the remaining space can't be reused in any way anymore, because the page always belongs to a table or index. So just think about it. Even by working on your table design, you can sometimes just fit more records onto one page of 8K, and therefore you can save some space. Again, space in your storage subsystem, space in your main memory in the buffer pool. So just think about it. So we have that storage overhead. We have already seen that. It's really, really worse in non-unique, non-clustered indexes, because we need that overhead for every level in that non-clustered index. And we have also seen that we always have in the leaf level of the non-clustered the unique identifier value as a lookup value. So that lookup value, the clustered key, is always needed in the leaf level. Otherwise, SQL Server couldn't perform lookup operations in the execution plan. Means navigating from the non-clustered index to the clustered index. Because the non-clustered, this is also very important to remember, in the non-clustered you just have a subset of your table. You just have a subset. You just have in the non-clustered your indexed columns. All the other columns, which are not part of that non-clustered, are by default in the clustered index, because the clustered index is your table. This is very, very important. Well, you can include columns in the non-clustered with the include keyword. Means with the include keyword, you have the possibility since SQL Server 2005, so already again, very long time. With the include keyword, you have the possibility to include columns in the leaf level of your non-clustered, not in the navigation structure. But what does it mean to include columns in the leaf level of the non-clustered? You are creating duplicate data. That included column is included or is stored in the clustered index, because the clustered index is your table data, and in addition, in that specific non-clustered, you're duplicating your table data to improve performance, because SQL Server doesn't have to perform that lookup operation. Means your read operations, your select statements are getting faster, but on the other hand, for example, when you change that included column, SQL Server has to update it 2 times. Once in the clustered index and also in the non-clustered index. And trust me, in the worst case, this can even lead to deadlocks. when you have a concurrent read and write operation on such a table. So a lot of disadvantages with lookup operations in SQL Server. If you want, we can make sometime a session about that topic. Would be also very, very interesting to show you how bad lookup operations could be in SQL Server. So as you see, we have a huge amount of disadvantages when we use unique identifier values as primary key values. As I've already said, size does matter. I've also shown you some comparison in a previous slide how bad it could be to use a very, very large clustered key versus a very, very small clustered key. Even performance matters. A page split just means that SQL Server has to do a massive amount of additional CPU cycles. Every additional CPU cycle that you execute takes some time, a few nanoseconds. Once a few nanoseconds, you can't feel it. But doing it over and over and over again, your performance will get worse. Every physical operation that SQL Server is doing during that page split must be logged in your transaction log. SQL Server can only commit your transaction when you have written all those transaction log records physically into your transaction log in your storage subsystem. So SQL Server can be only as fast as your transaction log. Just think about it. The more you write into your transaction log, the slower your database will get for write operations. Imagine you are using SQL Server availability groups in a synchronous mode. You have to send those transaction log records to your synchronous secondary replicas. When they are hardened in the transaction log of a secondary replica, SQL Server can commit that transaction on your primary replica. So even in that case, with availability groups, page splits are a really, really bad idea because you're introducing an overhead within your transaction log. And when you're using high availability technologies like availability groups, which are based on the transaction log, you will get a worse performance. So just think about it. So let's have a look on that one. So let's create again when we have connected to SQL Server. Let's create again a bad table. Again, we use a unique identifier value as a primary key clustered construct. Let's insert 10,000 records into that table. Let's check again our index fragmentation through systemdb index physical stats. With 10,000 records, as you can see, our table consists, or our clustered index consists of two levels. We have again our index root page, and we have some pages in the leaf level. SQL Server even tells us here how many pages we have. So when we have a look on that one, you can see we have 105 pages. We have a huge external fragmentation, means those pages are logically ordered in the leaf level, but physically they are just stored out of order in your storage subsystem. This happens because of the page splits. Imagine you have inserted the last page in that index, and then you have allocated somewhere in the middle of the index a new page. That page is stored somewhere else in your data file, out of order. And that leads to that external fragmentation that we can see here. And in addition, again, those pages of 8 kilobyte are full at around 65%. So 35% of the page is currently free, unused space. The same as I've said, when you're inserting into a phone book a new record, you have to allocate a new page. You insert into that page that record, and the remaining part of that page just stays empty. And the same concept applies here to page splits in SQL Server. Let's do the same with an int identity column. So we are just dealing with an int column, 4 bytes, very, very small, and int identity ever increasing. So we're just inserting rows at the end of our index. It's the same when you have a phone book and you're just inserting records at the very end. Just people which are starting with a set. A very simple, efficient operation. But you have to make sure that you're inserting records at the very end, which would be with a phone book quite hard. But with an int identity column, it's guaranteed because it's ever increasing 1, 2, 3, 4, 5, 10, 100, 1000, and so on. Just ever increasing. Let's insert into that table now 10,000 rows. Again, we have the same amount of rows. Let's check our index fragmentation. As we can see, our external fragmentation, previously it was nearly at 100%, 1.8%. Average page space used in percent, nearly 100%, means those pages are full at nearly 100%. Makes sense. We allocate a new page at the very end of that index, and then we are writing with an ever-increasing clustered key value onto that page. When the page is full, we allocate a new one. We write insert records ever-increasing on that newly page. Means those pages are used as efficient as possible. And as you can see, we have a page count of 55. Previously, we had a page count of 105. So that table is nearly half the size, because we can make, or we can fill those pages as efficient as possible. Just think about it. So as you can see from that demonstration, it makes a huge difference on which column you are creating your primary key constraint. And as I've said, the primary key is just enforced by an index, a unique clustered or a unique non-clustered index. And if you're using a clustered index for your primary key constraint, you have to make sure that you are not generating here page splits, because page splits are just messing up your whole table. Imagine now we have a bad table. So we have a bad table in production. We have unique identifier values. How can we deal with that problem? When we are starting from scratch, it's quite easy. By now we know unique identifier values are bad as primary key values or in combination with a unique clustered index. So the easiest way when you're starting from scratch is that we just enforce the primary key as a unique non-clustered index. And then we create our clustered index on a different column, which gives us a uniqueness and which is ever increasing. Problem solved. But what you are doing when you have an existing database table which has those problems, more or less we have two options. The first option is you are working with the so-called fill factor. When you create a new index or when you rebuild an index, you can specify a so-called fill factor. That's just a percentage value. And that percentage value just defines how much space should be filled on every page during the rebuild of the index. Imagine you use a fill factor of 50%, which is bad, but just for demonstration. A fill factor of 50% means we are filling up the half of the page, and the remaining half of the page stays empty. Means your table after the rebuild is the double amount in size, because 50% of that table, of that index, are now free space. What happens when you're inserting with a random clustered key value? Well, nothing, because you have some free space. Imagine you have a phone book, and in that phone book, every page is only full at 50%. When you try to insert a new last name like Aschenbrenner, quite simple. You just write that name into your phone book because you have some free space. Just think about it. And the same thing gives you the fill factor. Of course, 50% is a bad thing for a production database. It's a percentage value, means the larger your index gets, the more and more space you are getting. So it makes a difference if your index has a size of 1 gigabyte or 100 gigabyte. 1% from 1 gigabyte is a few megabytes. From 100 gigabytes, it's a whole gigabyte. So just think about it. So normally when you're working with the fill factor, you are starting with a very high fill factor value, like 95% or something, or even higher when you're dealing with very, very large tables. But the great thing is, with a fill factor, you can transparently avoid page splits up to a certain point in time. Because at some point in time, you have filled up your pages, means you have no free space anymore, and then SQL Server again has to perform page splits. And that's again the point in time when you have again to rebuild your indexes. So you have to monitor when page splits are kicking in, and then you have again to rebuild your indexes with a lower fill factor of 100%. But it's completely transparent, means the fill factor is more or less for the database administrator, the DBA, default blame acceptor, as we say. Or the second option for developers is that we just enforce the primary key value with a unique non-clustered index. When you create with a new table, or when you start with a new table, it's quite simple. You just specify primary key non-clustered. But when you have existing tables, it's very, very hard because you have to do a lot of different things, as you see in that list. So let's have a look on both things. Let's start by talking about the fill factor.
And I hope that people are sticking with us. We are a bit over time, and I know that we are about to be done. So yeah, hang in there, and we'll be done in a few minutes.
I'm trying to talk as fast as possible.
That's fine.
Perfect. So let's create a new bad table. Again, the same bad things as previously. Let's insert now 50,000 records. Takes a little bit longer, but it makes the table a little bit larger, and therefore the fill factor just have more impact on that table. So when we have inserted those rows, we again check our index fragmentation, and we see the same things as previously. We have a bad external fragmentation, we have a bad internal fragmentation, and we need more than 500 pages for 50,000 records. So all the bad things from previously. What we are doing now, we are just rebuilding our clustered index that SQL Server has created in the background for us with a lower fill factor. So I'm just getting here the name of the clustered index that SQL Server has created for the primary key constraint. I'm passing that in here, and now I'm just specifying the fill factor of 50%. As I've said previously, please make me a favor. Please do not use 50%. Even don't use 90%. It means 10% would be free space. Just start with a very, very high value like 95% and then just monitor how SQL Server behaves. Let's rebuild that index with a fill factor of 50%. Let's check now the size of our clustered index again. Of course, you think now with 50%, the table is 100% larger. Let's check that. Let's check that. No, it's not larger. We have a page count of 705 pages. Previously, we had 500 and something. Well, previously, we had an internal fragmentation of around 65%. Means we had already somehow a fill factor of 65% or 35%. Just think about it. The internal fragmentation is more or less the current fill factor of your table. Means when we have rebuilt it now here the index with a fill factor of 50%, the table doesn't get the double in size. Already free space in that index. This is very important to remember here. And now the great thing is we have 705 pages, average page space used in percent 50%, and average fragmentation in percent. The external fragmentation is currently 0%. Means the logical and physical sorting order of those pages in the leaf level of the clustered index are just the same. Let's insert 10,000 rows. Let's check our index fragmentation. External fragmentation, 0%. We had no page splits. We still have 705 pages. Means for those insertions, SQL Server hasn't allocated any page because we had free space. And as you can see, average page space used in percent is now 60%. If we insert 10,000 rows again, we are going up to 70%, 80, 90, 100%. And then page splits are again kicking in. And those page splits are again leading to internal and external fragmentation. So the fill factor is one very simple, efficient way for a DBA to overcome that problem. And the second option for developers is that we are using or that we are enforcing primary key constraint as a unique non-clustered index. Imagine instead of specifying here primary key clustered, we specify primary key non-clustered. Let's try that. We have created that table. And now we have specified that the primary key constraint should be enforced as a unique non-clustered index. So the question is, what kind of table do we have now? Well, as I've said initially, SQL Server supports two kinds of tables, clustered tables or heap tables. So when we look now into these indexes, for that specific table, we can see that we have no clustered index. Oops. We are dealing with a heap. Type description is heap. And index ID 2 our first non-clustered index is a unique one, and that unique one is used to enforce the primary key constraint. Means when we go down now, you can create your clustered index on a different column. Of course, last name is here a bad example, but imagine you have some ever-increasing values in your table definition. Date values like an order date. An order date is normally ever-increasing. You are making orders just in the future, not in the past. So even an order date column would be a great candidate for an ever-increasing clustered key value. So let's create that one. When we look again into sys indexes, SQL Server has swapped now the heap table for a clustered table. But that clustered index, as we see, is not used for the primary key constraint. The primary key constraint is enforced through the unique non-clustered index that we have created previously. This means now, when we are making insertions into that table, we have moved our index fragmentation from the clustered index into the non-clustered index. So when we insert here 10,000 rows, and we check the index fragmentation, we see in the clustered index, that's the leaf level, the second one, we have no external fragmentation. In the non-clustered, we have external fragmentation, and when we look on the internal fragmentation, you see the first one was clustered. Yeah, in the clustered we have more page space used as in the non-clustered. So more or less we have moved now the index fragmentation from the clustered index into the non-clustered. But who cares about the non-clustered? Nobody, because the non-clustered index in that case is just a non-clustered which is used to enforce the primary key constraint. That's very, very important. And that's the preferred option when you deal with unique identifier values as primary key values. Just create the primary key constraint as non-clustered, so that you're just moving all the problems from your clustered index away into a secondary non-clustered index. And in that non-clustered, you don't care about those problems because you are not accessing that non-clustered. That non-clustered is just a supporting index to make it possible to enforce the primary key constraint through it. So that's very, very important here. So by working on your table design, you can get that problem under control. Okay, so we are now finished, already a little bit later as planned. The last time when I have presented that topic, I have talked for 2.5 hours. Therefore, I have also asked you today in the morning, Brian, how much time I have. So I've already stripped down that presentation because I have seen from the MS Teams invite 75 minutes. Okay, this is less than 2.5 hours. So that was the reason, just to be sure and to be on the safe side. So over the last 1.5 hours, I have gave you now an introduction about clustered indexes, non-clustered indexes, and the very important concept or takeaway from that section is that we have a strong dependency between both indexes through the clustered key. And normally the clustered key is just the column on which you are creating your primary key constraint. And therefore it's very, very important when you have a primary key column which doesn't give you ever increasing values, that you are enforcing that primary key constraint with a non-clustered index, as you have seen in the last demonstration. Or if you don't have that possibility, you can work in a transparent way through the fill factor. But as I've said, the fill factor only applies during index rebuild or index creation statements. So afterwards, your pages are filling up and up and up again, and at some point in time, page splits are kicking in again, and then you have to rebuild your indexes again. Cool. If you want to know more from me, I'm doing an upcoming online training in April 4, a webinar about SQL Server query tuning fundamentals with a lot of stuff around query tuning in SQL Server. I'm also talking here about indexing, execution plans, how you can use that information in the execution plan to improve your queries. You can find here further information on my website, and I can also give you a discount of 10% if you're interested. Just send me an email and we will get those things sorted out. Cool. So thanks for attending my session tonight. I hope that you have enjoyed it, that you have learned hopefully a lot from me, and maybe we will see each other online or physically at some conference again. So thank you and enjoy the remaining part of your evening.
Thank you, Klaus, and thank you for attending this session.
Thank you.
You get a lot of comments on the chat. You have one from Thomas in Deutsch. Vielen Dank, Klaus. Detailliert und interessant, wie immer. And then from Marcus, thank you very much for your time. And also from me, of course, Klaus, thank you for coming. Thank you for presenting to us. And I hope you all got something out of it. I learned a lot today. I didn't know that small feature to remove the primary key out to a non-clustered thing. So thank you, Klaus. And so I hope you have a great evening, and hope to see you soon again.
Okay. Thank you.
Thank you.
Bye.
Bye.